children, how are you all? I hope all of you are fine. So we are ready with our new video. So before that, let's do some warm-ups, right? Okay, snap your fingers. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's begin. So in the last class we have spoke about Euclid's division lemma, how to solve the problems, how to forget about our old system of division and learn a new system, by a new system of division, how to divide a number we have seen, and we have also seen how we can use Euclid's lemma to find HCF of any number, right? Now let's proceed with the chapter, second part of real number. Now we know there are two kinds of numbers, right? One is prime and another is composite. Now what are prime numbers? Prime numbers are numbers which have two factors. Now what is a factor? Can you say me? What is a factor? Factors are numbers by which if you divide the number you get remainder as 0. Okay, so prime numbers have two factors. What are those? One is 1, the number 1 is the factor, and number 2 is the number itself. Okay, so what are prime numbers? Numbers which have two factors. What are factors? Factors means by which if we divide that number we get remainder as 0. There are two factors of a prime number. One is 1, another is the number itself. Okay, similarly, what are composite numbers? Numbers which are not prime. Okay, which means numbers which have more than two factors. Okay, numbers which have more than two factors. Now let's see what are these example of prime numbers. Example, you can say 2, 3, 5, etc. Okay, now why am I saying 2, 3, all these things? Now see, 2 has got only two factors. 2 is equal to 2 into 1. That means the number itself, 2 is the number, then the number itself, 2 is a factor and 1 is a factor. Do you find any other factor for 2? No. Similarly, for 5 also, you see 5 will always be 5 into 1. Do you find any other factor? Any other number that can divide 5 other than 5 or 1? No. So that means 5 also is a prime numbers. For composite number, let's see what are its examples. Examples are like, suppose 4, 6, 9, okay, etc. Now why am I saying 4 as a composite number? Because how can we get 4? 2 into 2, okay, then 4 into 1. So how many factors are there? 2 is a factor, 4 is a factor, and 1 is a factor. So means greater than, then number of factors are, number of factors for 4 is greater than 2, right? Number of factors are greater than 2. For 6, let us see. See, for 6 you can get 2 into 3, 6 into 1. So how many factors are there? 1, 2, 3, 4. So this is also greater than 2, right? For 9, let us see. 3 into 3 and 9 into 1, which means again it is having 1, 2, 3, which is greater than 2. So that means prime numbers are numbers which have only 2 factors, whereas composite numbers are numbers which have more than 2 factors. Okay. Now you may ask me a question that, ma'am, we have already learned prime numbers, composite numbers in your junior classes. Why are we going to learn this now? Okay, we are in class 10. Why are you going to learn all these things? See, because you have to know that every number can be expressed as a product of its prime factors. Okay, every number can be expressed as the product of its prime factor. Now this one, if you think, you will see, suppose if I say a number as 14. Okay, 14 is a common number that you know. Okay, now how to express this as a product of, I told, prime factors. Okay, so it will be 7, 2. So that means I am expressing it in product of its prime factors. Now let me take another number like 26. Okay, I'm taking another number as 26. Can this be expressed as a product of its prime factors? Okay, first prime number, what? As it is an even number, we'll start with 2. Okay, it will come as 1, 3. See, again, it can be expressed in the product of its prime factors. Now I'll take one bigger number. Okay, like 145. Okay, now let's see if this can be expressed as the product of its prime factors or not. So as you see, 5 is there, so we'll start with 5. Okay, so how many times? 2s are 9s are, right? So every number you see can be expressed in the product of its prime factors. So we can say 14 is equal to 2 into 7. Here we can say 26 is equal to 13 into 2. Here we can say 145 equals to 29 into 5. Right. So this thing is stated as a theorem. Okay, and that theorem is known as fundamental. It's very easy. Okay, fundamental theorem of arithmetic. Those who fear maths, for them it's very easy. There's nothing to get afraid of maths. Okay, it's very easy. This is known as fundamental theorems of arithmetic. By hearing the name fundamental theorem of arithmetic, you may say, oh my god, so big name, what is it? But it's nothing. It's the thing that is there in the stated in the theorem, you all know from the beginning itself, that every number can be expressed as the product of its prime factors. Okay, here every number means, not every number means here prime numbers. Okay, here every number means composite numbers. Okay, prime numbers obviously has only 2 factors, the number itself and 1. Okay, so every composite number can be expressed as a product of its prime, and this occurrence of the prime number in the factorization, that this process is known as factorization. Okay, this finding of the factor is known as factorization. So this process is unique. Okay, it is not similar with one another. The occurrence of 2 or occurrence of 5 is not similar to each and every number. Okay, so this is known as fundamental theorem of arithmetic. So what is the fundamental theorem of arithmetic? Please note it down. Every composite number can be expressed or factorized as a product of primes, okay, prime numbers, okay, and the factorization is unique apart from the order in which prime factors occur, which means factorization means what? Like the way I showed you, stepwise division method, okay, and the occurrence of the prime numbers, like first 2 will occur or 3 will occur, after how many times 2 will again occur in the division, that is unique. Okay, that every number has a unique thing. That is nothing to do with any other that has nothing to do with the other numbers. Okay, so it is apart from the order in which prime factors occur. Now suppose I have a question that consider a number 4 to the power n where n is any natural number. Okay, we have a number 4 and it is having a power as n. N is any natural number. Okay, is it possible that 4 to the power n will end with 0 for any value of n? Is it possible that 4 to the power n, okay, that means suppose n is equal to 1, okay, what it will be? It will be 4. Okay, so suppose if I say n can be anything starting from 1 to infinity. Okay, now if I say, as because it is a natural number, if I say 4 is equal to 1, it will be 4. 4 is equal to 2, it will be 4 4s are 16. Okay, like that 4 is for any like powers, okay, 1 2 any number. Okay, is it possible that 4 will have a 0 at the last instead of, suppose here like 4 to the power 2 is having 6 at the last. Okay, for any number of n, is it possible for 4 to the power n to have a 0 at the last? Now see, if a number is having 0, okay, suppose a number is x is having 0, okay, at the end, that means what? Which prime number will divide that number, or what will be its factor? One factor must be 5. Okay, 5 will be one of the factor. One of the factor will be 5. Okay, for a number to be 0, having 0 at the last, one of the prime factor have to be prime factor. Okay, not just any factor, because 0 10 also can be a factor. Okay, for a number having 0 at the last, so prime factor 5 must be there. Okay, but now see, if we write 4 to the power n, okay, what will be 4 means what? 4 means, again we know, 2 into 2, right? So 4 means what? We can write 2 into 2 to the power n, or we can write 2 to the power 2 n, or we can write 2 to the power 2n, right? So anywhere can you find 5? No, we can't find 5 over here, which means that it is not possible to have 0 at last. Okay, for number 4 to the power n. Okay, n being any natural number. We will go back to our junior classes, okay, and we'll see how we have done prime factorization. Okay, let us take a number. Let us take a number like 256. Okay, let the number be 256. Now we will factorize using prime factorization method. So first, as it is an even number, we'll try with the first prime number, that is 2. So what it will come? 1, 2, 8, right? Because 1 2 is a 1, then 4. Okay, 4 means 2, 2 2s are 4, and 1 comes as remainder, then 16, 8 2s are 16. Okay, next again by 2, 6, 4, right? 6 2s are 12, 4 2s are 8. Then again by 2, 32. Then again by 2, 1, 6. Then again by 2, we get, see, 16, 32 all can be divided by 4 or 8, but I am not using that. I am using only the prime numbers. Okay, so 16 means 8 2s are 16, so 8 again by 2, it will come as 4, and again by 2, 2 2s are 4, right? So we can say 256, we can express this as, how many 2s are there? 1 2 3 4 5 6 7 8. So 2 into 2 into 2 into 2, 8 times I have to write, no? So why will I do that? I am in class 10, no? So what will I write? 2 to the power, instead of this I'll be writing 2 to the power 8, right? Okay, let's take another number. Let me take another number like 726. Okay, I'll do prime factorization. So 2, 3 will come, right? 3 2s are 6, 1 comes as remainder, so 6 2s are 12. Okay, and 6 is there, so 3. Now this is an odd number, but it can be divided by 3. So what can I write? 1, 2 and 1. 121. Now see, 121, this can be factorized by 11. 11 is a prime number. So what can I write? 1 and 1. Right? So what can I write? 726 is equal to 2 into 3 into 11 into 11. Shall I write like this way? Like this way, children of 4, 5, 6, 7, they write. Okay, how will I write as I am in class 10? 2 into 3 into 11 to the power 2, right? So this is the method of prime factorization. You see, the number of occurrence of the prime numbers, this is unique. Okay, no one can formulate it in any of the formulas. Okay, that when will this come, when will that come, how many times will one prime factor come, or how many times a prime factor will not come, that is unique in all cases. Now let me give you two numbers. Okay, 24 and 36. Okay, and I tell to factorize these two numbers using prime factorization method. Okay, so 24, what it will come? 2s are 12, 2s are 6, 2s are 3. Okay, and 36, 2s are 18, 2s are 9, 3 is a 9. Right? Now this one can be expressed as 24 2 to the power 3 into 3 to the power 1, and this one can be expressed as 36 can be expressed as 2 to the power 2 into 3 to the power 2. Right? Now from here, if I tell you to conclude HCF and LCM, if I tell you to find out what is the HCF and LCM, can you find out? Yes. HCF means what? Highest common factor. See, among see the factors of this number and this number. What is the highest common thing in this one? 3 to the power 1 and 2 to the power 2. Right? So HCF will be of 24 and 36 will be 2 to the power 2. Why 2 to the power 2? Again I am telling, because here I have 2 to the power 3. That means 2 to the power 2 into 2, which makes 2 to the power 3. Right? So 2 to the power 2 into, here I have 3 square, here I have 3 to the power 1. So I'll take 3 to the power 1, because 3 to the power 1 into 3 to the power 1 makes 3 to the power 2. So this is there. Okay, so which means 2 square means what? 4 and 3, so 12. Okay, and for LCM means what? Least common multiple. Okay, least common multiple. So what is the common, we will find out what is the highest power of prime factors we have. Like here we have 2 to the power 3, and here we have 2 to the power 3 to the power 2, which means 2 to the power 3 means what? 8, and here it means 9, which means 9, 8 9s are 72. Right? So in this way, by using prime factorization method, we can find out HCF and LCM of two numbers. Now let us multiply these two numbers, okay, like 36 and 24. Okay, what it will come? $864, right? 864 is our answer if we multiply these two. Okay, now you see whatever LCM or HCF we have got, now let's multiply those two. Okay, I'm multiplying over here. We have 72 and 12. Okay, 4 14, then 72 again, so 4 6 8. Oh my god, we are having same, right? Both the products are same. So here, from here we can conclude, we can come to a conclusion that HCF of two numbers, let that be A and B, and LCM of two numbers will be equal to product of the numbers. HCF of two numbers and LCM of two numbers will be equal to product of the numbers. Now suppose you are given two numbers, okay? How many types of question can come? Okay, first type is you are given A and B is given, A and B and HCF is given. Then how will you find the LCM? Simple, A into B by HCF. Similarly, if A and B is given and LCM is given, how will you find out? A into B by LCM, right? And if HCF and LCM is given and you asked about the two numbers, okay, asked about the two numbers, product of the two numbers, how will you get? You will just multiply HCF into LCM. Is that clear? Okay, so thus we come to the end of this lecture session, today's lecture session, and at the end I have given you one assignment. This is assignment number 2. Find the I have 5 questions I have given. I am reading it out. Find the factors of number 3264 by prime factorization method. Question number 2. Consider a number 9 to the power n where n is a natural number. Is it possible to have 0 as the n digit for 9 to the power n for any value of n? Just as I have shown, no, 4 to the power n. Similarly, you have to find, you have to break, you have to find the base, and then you have to proceed forward. Okay. Third one is very easy. Find HCF of 510 and 92 by prime factorization. Fourth one, find LCM of 26 and 91 by prime factorization. Also, you have to prove that you have to verify LCM into HCF is equal to product of two numbers. That means you have to find out 26 and 91's LCM. Then you have to find out HCF of the two numbers, and then you have to find out product of two numbers is equal to them or not. Okay, product of LCM or HCF or not. And fifth one, given HCF is 306, HCF of 306 and 657 is 9. Okay, and you have to find LCM. Don't forget the formula I have said. Okay, and then two numbers are also given. Okay, from here you have to find it out. So all the best, and we'll be coming up with a next video, okay, in the next class. Okay.